Okay, for today's class activities, we're going to do chapters 10, 1 through 3, and cover concept questions 1, 2, 3, 4, 5, and 6, and exercises 2, 11, and 19. Okay, so you're going to want to go and read this thoroughly so that you're comfortable being introduced to the concepts and allow these problems to reinforce those concepts in your mind. So we're going to step through this one at a time. Go ahead and take a look at concept question 1. All right, so the question is, what basic quantity does kinetic energy depend on? The answer is velocity. I like to say kinetic energy is the energy of motion. Okay, kinetic energy truly is, if it's moving, it's got kinetic energy. Okay, so this depends on the velocity, specifically the velocity squared. It also depends on the mass, but more so it's an object with mass doesn't itself have kinetic energy. It has to be moving to have kinetic energy. All right, so what does potential energy depend on? Well, potential energy could be multiple different things. It could be gravitational potential energy, chemical energy, but it's an energy of interaction. And often is a function of position. Even in chemical energy is based on bond strengths, which are highly determined by their positions relative to each other, which are themselves determined by the chemical structure. But gravitational potential is dependent on the vertical position. Spring potential energy is based on the bonds in the spring itself, how pulled apart they are, or how pushed together they are relative to their equilibrium lengths. So it's an interaction, and most often depends on position. Okay, number 2, go ahead and look at that one. See, based on these definitions, what can you say about number 2? Can kinetic energy ever be negative? No. Kinetic energy is, in equation form, 1/2 mv squared, but we just said it's the energy of motion. Okay? Can you have negative motion? I can move backwards, I can move forwards, I can move up, I can move down, and I can choose those directions to be positive directions. But it's not an energy of direction, it's just an energy of motion. And so even though I'm moving left or down, and I've chosen those to be negative, I'm still moving. And so kinetic energy can never, ever be negative. It has to be greater or equal to 0. All right? And that's something that you can really hold on to in this course. So what about potential energy? Can potential energy be negative? Yes, it could definitely be negative. Gravitational potential energy could be negative. So if I choose the ground to be 0 with y measured up, and I drop a ball into a hole, well, that's below 0, so it's got a negative y value, so it's got a negative energy. So Ug is mgy, and that depends on your position, which depends on where you've placed your origin. So it can be plus or minus. It could be negative. All right, let's move on to number 3. Okay, so we've got a roller coaster that obtains a speed v0 when it goes down a hill, and the question is, how much higher should the hill be in order to double the speed? So in this case, we've got our kinetic energy is turning in, or sorry, got it backwards. Our gravitational potential is turning into kinetic. It starts with, we could choose the lowest part of the road track to be 0. So it's all potential to start and then all kinetic to end. We're assuming it starts from rest. And so we have an mgh equals a 1/2 mv squared. And so how does the velocity depend on the height? Well, we're arranging that the velocity is going to equal the square root of 2gh. So in order to double the speed, how high do I need to make this track? I'd have to quadruple the track height because I'm going to end up squaring that 4 to give me the 2. So I'd have to quadruple h in order to double the speed. Okay. All right, number 4. Go ahead and take a look at number 4. Okay, this is a really good problem. If you tried to solve this problem with kinematics and dynamics, you could do it, and you'd come up with the same answer you would with energy, but it would be a pain in the rear. It would be all sorts of complicated stuff. So just to make sure it's clear, we have this ball, and in case A, we throw it straight up with the speed v0. In case B, we throw it straight down with the speed v0. And in case C, we throw it horizontally with the speed v0. So in all those cases, the initial kinetic energy is the same, okay, because our K initial is 1/2 mv initial squared, and in all those cases it has the same kinetic energy because it has the same speed. And the question is, well, what's going to be the velocity, total velocity? Note, it doesn't say the y velocity or the x velocity, it just says the velocity when it hits the ground. Okay? Well, that's going to be K1, 1/2 mv1 squared, so that's what we're looking for, but it's buried inside the final kinetic energy. Well, that's a change in kinetic energy, and if we choose the Earth to be inside our system, then that change in kinetic energy is going to be equal to the negative change in gravitational potential energy. Okay, and they all start at the same height, so this is equal to negative mg delta y. They all start at the same height. They all end at the same height. So according to our energy analysis, they all have the same final speed. Even though I throw one straight up and one straight down, doesn't it seem like the one going straight down would be faster? Well, with a little bit of thought and a little bit of your experience, you can say, well, wait a minute. I guess when I do throw a ball up, it slows, reaches a height, and speeds back up. And by the time it reaches my hand again, it's going as fast as it was when I threw it, but now downward. So A and B are, I guess, the same thing. That seems reasonable. But what about C? You know, when I throw a ball horizontally, okay, the speed that it hits the ground, the y component's not nearly as fast because there's no speed in V to start. But you have to remember, when that ball's going that way with speed v0, it gains, so it gets down here, and it's got a speed down here, so v1, it gains this much, this is v1y, and maintains this much, that's v0, which would be the x component of v1, right? Because this never slows down, and so it gains this amount. This one's harder to see, but you could again use kinematics and dynamics in a two-dimensional projectile problem to find the size of this one, and then if you take the square root of the sum of this squared plus this squared, you would get the same number as you get following these energy analysis. And it's a lot easier. Energy, this is an example that I love because it shows how much more powerful or much clearer energy can be in analyzing systems. Okay, so again, they will all have the same speed because their change in y is the same, therefore the change in potential energy is the same, therefore their change in kinetic energy is the same. All right, let's go and move on to number 5. Okay, so what's the definition of potential energy in a spring? It is U spring equals 1/2 K delta S squared. What is delta S? It's the stretch or compression. Okay, it doesn't matter if you stretch it or compress it. It just matters about how much. Okay, and K is the spring constant. So in case A, our USP for A is 1/2 K d squared. It's compressed to distance d. In case B, it is stretched now a distance d. Okay, does that matter? Nope. I don't care if it's compressed or stretched, as long as it's just the displacement of the end. Okay, so they have the same amount. And what about USPC? In this case, it's just got a constant that's 2K and it's stretched to distance d. Okay, so that's twice as big just because it's linear in the spring constant. And then finally we have USPD, which has a normal spring constant, but it's stretched twice as much. So we have 1/2 K 2D squared, and that becomes a 1/2 K 4D squared. And the 2D was quantity squared. And so this is now 4 times as big as A or B and twice as big as C. So again, thinking about the proportionality, but being specific is this delta S is stretch or compression. It doesn't matter. Okay, well, let's move on to number 6 now. Okay, you compress a spring 1 centimeter. How far must you compress a spring with twice the spring constant to store the same amount of energy? Now think about what we just did here with this definition. How can you apply it to this problem? Right, so if we just write a U0 equals a U1, we want the potential energy to be the same. So this would be a 1/2 K0 delta S0 squared equals 1/2 K1 delta S1 squared. Okay. And we double the spring constant in this case. So this becomes a 1/2 2K0 delta S1 squared. So we can cancel the halves, cancel the K0s, and I get delta S0 squared equals 2 delta S1 squared. So how much does delta S need to change? Well, if I solve for delta S, I'm going to get square root of 2 times delta S is 0. So it's going to have to be square root of 2 times the 1 centimeter. All right, let's move on to some of these exercises. Okay, consider exercise 2. Okay, a system of 2 objects has a delta K total of 7 joules and a delta U internal of -5 joules. Now we don't know what kind of potential energy this is, but it's just internal to the system. So the question is how much work is done by the interaction forces and how much work is done by the external forces. So let's write out our energy equation that we have so far. The work external is equal to our delta K of our system plus our delta U of our system. I'll go and put internal to emphasize that's inside our system. All right. So how much work is done by the internal forces? The answer is 0 because they're inside. So W U internal or F internal equals 0. So this is more so catching on cataloging the effects of your forces correctly. If we choose it to be a potential energy inside our system, then it cannot do work on our system. All right, but what about the work done by forces outside, okay, external to the system? Well, that's this number. That's what it means. And so we can plug in the 7 joules for the first case, and then a -5 joules for the second case, and that gives us a total of 2 joules. So work done from outside forces is just the numerical outcome of this side. All right, number 11, go ahead and apply this. So this is about gravitational potential energy. Okay, this is a car, goes down a valley and up a hill that's a little taller on the other side. Here's state 0, here's state 1. This has a height of 10 meters. This has a height from the lowest spot of 15 meters. It's moving at a speed v, and it's got a mass m. And it just barely runs out of gas and decides to coast, which means it's not slowing or speeding up. There's no friction, and there's no driving force nor braking force. So it's now just going via gravity through that hill. The question is, how fast is it going when it gets to this gas station on the other side? How do you do that? Well, let's employ our general energy equation. Okay. Now, if there are no external forces, so if I choose my system to be everything, And by saying everything, I'm saying the car and the earth. There's nothing else that's interacting in change. There's no friction. That's not slowing it down. So by saying that, my work external is 0, and therefore that leads to me being able to say that my kinetic energy initial plus my potential energy initial equals my kinetic energy final plus my potential energy final. Okay. All right, so I'm trying to find this one. How fast is the car going when it's done? So how do I solve for that one? All right, if I solve for that one, first of all, I don't see any of these that are 0, okay, because according to the coordinate system I've chosen, with 0 being at the base of the valley, I start with a height and I end with a height. I'm starting moving and I'm asking for how fast am I going when I get there. So these are all non-zero. So I just need to solve for it. K1 is then going to be equal to K0 plus UG0 minus UG1. Okay. I'm just going to rewrite that this way. K0 minus UG1 minus UG0. And the reason I'm doing it that way is because 1 minus 0, that's delta U. So it's saying that my final kinetic energy is equal to my initial kinetic energy, subtract the change of potential energy. And since UG1 is bigger, then I'm subtracting a positive number, which makes sense. I should be going slower when I get up here because I had to go higher up the hill. Okay, so now I can just solve for the velocity. And then dividing by m everywhere. You see, I don't need to know the mass. Multiply by 2 and taking a square root, which I'll let you do. But you're going to end up with a velocity of 1.41 meters per second, which seems reasonable for the initial speed of 10 meters per second, and it had to go an extra 5 meters higher than it started. So it should be smaller than the 10 meters, but of the right order. Okay, last problem, 19. Okay, so we have a cart, a grocery cart, and it's run away. So it's moving across the parking lot, and there's a spring attached to a car or a building or something like that. And here's our initial case. And in our final case, the cart has stopped and it's compressed the spring. So in this case, we have a V0 and a delta S0. In this case, we have the V1 and a delta S1. And the question is, how fast was the cart going if it compressed the spring by 60 centimeters? Okay, so how are we going to do this one? Well, this is an energy problem again. If I choose my system to be the cart and the spring, I don't need to worry about gravity in this case because it's moving horizontally. There's no change in vertical position. So by doing that, it basically said everything that's interacting. And so the kinetic energy plus the potential energy start must equal the kinetic energy plus potential energy final. So I can say K initial plus U S initial equals K final plus U S final. And so now we go through and say, okay, well, what do I know about these? It is moving, so that's non-zero. Is the spring stretched or compressed before the cart hits it? No, it hasn't hit it yet, so the spring is just sitting there at its relaxed length, and so even though it has a length, it could be a meter long, that doesn't matter. It's just how much is it compressed or stretched relative to its relaxed length. So before the cart hits it, it's not, so this is 0. Okay, and then once it fully compresses that, it has stopped. So this is 0. And so our initial speed, or initial kinetic energy, which we can write out as 1/2 mv0 squared, is simply equal to the final potential. Or in other words, the kinetic energy has turned into spring potential energy. It's been transformed from one form of energy to another. This is 1/2 k delta S1 squared. Now we can just solve right out there those. And we get a square root of k over m times the delta S1 squared. Oh, sorry. I took the square root, so that's gone. Plugging your numbers, you get 3 meters per second. About 9 feet per second. Sounds reasonable for a runaway cart.